Okay, so today we're going to talk about a different type of differentiation, which is known as implicit differentiation. And this concept is actually very, very important, and we'll use this quite a bit in the sections to come. So if we were to kind of start off with this, the first comment we'll make is this. So we have thus far differentiated explicitly. And what I mean by explicitly, some examples would be such as y equals to x squared cosine of x, or y equals to x to the fourth plus 3x to the power of 10, and so on. And so what does it mean that we've differentiated explicitly? What that means is we basically, if you look at all the equations, they're all in terms of y equals, and then everything is in terms of x. So what we notice is y is a function of x. Notice how y is on the left side and it equals to some expression in terms of x. So when you say an equation is written explicitly, that means it's written as y equals something in terms of x, or basically one variable equals to something in terms of another variable. Okay, so they're not kind of mixed up. So then the next question becomes, well, now the question is, how would we differentiate a function of the form x cubed plus y cubed equals to 6xy? Okay, and so technically speaking, as far as the skills we have right now, you would probably try to grab this and solve for y just so you can get y equals and something in terms of x, which good luck doing that, right? If you look at this, you can't do that. So just because I can't solve for this explicitly, it doesn't mean that I can't find the derivative. And this is where the cool part comes in. It's kind of like, okay, I can't solve for y, so how am I going to find the derivative? And this is where implicit differentiation comes into place. So in fact, even if I can solve for y for this, I don't even want to waste my time solving for y. If you ask me to find a derivative of this and I see that the x's and y's are all mixed together, I'll go ahead and solve for, I could find the derivative of this without necessarily having to solve for y. One other comment I'll make in this class, and I'm sure just anywhere else, anytime you see an expression in terms of x's and y's, we always assume that x is the independent variable. Okay, so y is always the dependent variable unless we're told otherwise. So if I tell you, hey, look, for this equation, y is the independent variable, x is the dependent, then you're switching your train of thought. But unless we're told otherwise, we're always assuming x is the independent variable, y is the dependent variable. Okay, and usually in the questions, you should be told what your independent and dependent variable are. But if you're not, always assume x is the independent variable. Okay, so a comment I want to make here is we do not need to solve for y. Okay, instead, the way we could find the derivative of this is we can use implicit differentiation to find dy dx. Okay, now remember, when you see dy dx, let's make a comment about this. Remember that dy dx means the derivative of y with respect to x. So in other words, what we're saying is y is my dependent variable, x is my independent variable. Okay, so what this means is, and one other thing I want to make a comment on. Let's kind of come back up here, okay? If we look at this, notice how we can't solve for y. So what is y? The thing is, we don't know what y is. In fact, y is some function in terms of x. I don't know what it is because we can't solve for it. Like in this example here or up here, y we've defined in terms of x. Over here, we don't know what y is, okay? Since x is my independent variable, the derivative of x is just 3x squared. But the derivative of y, we have to be careful about that because we don't know what y is or what function y is. So y is something that is some expression or some equation in terms of x, which we don't know. And so we'll talk about how we'll take that into consideration. Okay, so coming back to this, by saying we want to find dy dx, or we want to find a derivative with using implicit differentiation. So what that means is that what we're going to do is we're going to say this means take the derivative of both sides of the equation with respect to x, and then solve for y prime. And when I say solve for y prime, see, once you find a derivative, the y prime or dy dx, which they mean the same thing, that will pop up. Now, this is if possible. Okay, so once you find the derivative implicitly, you might not be able to solve for y prime. So then you just leave it as is, okay? But if possible, we want to solve for y prime. So let's make a couple of comments about this. So when we're using implicit differentiation, there's two comments I want to make here, which the first one I've already talked about, but we'll put it in our notes. We will assume that the given function equation determine y as implicitly as a differentiable function of x. So in other words, what we're saying is that we don't know what y is. Y is just some function in terms of x. And we don't care to find out what y is because we're going to use implicit differentiation, okay? But keep in mind that something's going to happen here, and this next comment is actually going to point that out. So in other words, y is a differentiable function of x means that y is a function in terms of x. And so what this implies is that we have to use the chain rule, okay? So here what we're saying is apply chain rule. And since the chain rule is so fun, I'm going to put an exclamation mark here, okay? Because it's kind of like you'll see what this means. So let's kind of elaborate on this a little bit. So when we're saying y is a differentiable function, so this is what we mean. Let me kind of give you an equation so you understand what we're saying here. So in other words, if I give you something like this, which is what I gave you earlier, x cubed plus y cubed equals to 6xy, see, what are we assuming? X is my independent variable. Y is a function in terms of x that I don't know what it is, okay? This is equivalent to the following. X cubed plus f of x cubed equals to 6x times f of x. Okay, which notice what's happening here. When I'm finding the derivative of this whole thing, the derivative of that is easy. It's just 3x squared. But the derivative of this, see, we don't know. See, y is f of x. It's just a function. We don't know what it is. See, I don't know what f is. It's just some function. So if I say find the derivative of f of x, you'll just call it f prime of x. But then again, here, how would you find the derivative of this? This is where the chain rule kicks in. You'd say the derivative of the outside, which you'd bring the 3 down, and then it would be 3 times f of x quantity squared, times the derivative of the inside, which gives you the f prime of x. Okay, and then here you'd use the product rule. Okay, so hopefully you're understanding what we're doing here. We're not solving for y, but we know if we were to solve for y, it would be a function in terms of x. So this means the same thing as that, and this is clearer to see as to how you'd find a derivative. Okay, so with that said, let's actually put implicit differentiation to use. Okay, so let's look at our first example. And for example 1, the point I'm going to try to make is whether you find derivatives implicitly or explicitly, they both give you the same end result, okay? Except you'll notice that if you're using implicit differentiation, or if the equation isn't given to you explicitly, then just use implicit differentiation because it's going to save you some time. So here's what we're going to say. For the function or the equation 4x squared plus 9y squared equals to 36, we're going to do this 2 ways. First way is find y prime by implicit differentiation. Okay, so basically we're saying, remember, y is the function in terms of x, so we're finding the derivative of this using implicit differentiation, which means just take the derivative of the left side and the right side and then proceed with it. The second method we're going to do here is we're going to say solve the equation explicitly for y and differentiate to get y prime in terms of x. So for this one, they're saying, okay, before you find the derivative, solve for y, then find its derivative. Which, notice how this equation that I gave you, we can solve for y. But you won't always be able to explicitly solve for y. But the reason why we've done this is I just want to show you that a and b, no matter which approach you take, after all, you're finding the derivative of this guy, aren't you? So it should be the same thing. And we'll show that it is the same thing, okay? So let's start off with part A, which is using implicit differentiation. So if we start off with 4x squared plus 9y squared equals to 36, we're finding the derivative of this. Okay, now remember, y is a function of x. X is my independent variable. So to find the derivative of this, we're going to take the derivative of both sides. So what's the derivative of 4x squared? That just becomes 8x plus the derivative of this. I have to use the chain rule because the derivative of the outside is this 2. I'm going to use the power rule. So bring the power down. So 2 times 9 is 18y to the power of 1 times the derivative of the inside, which the inside is y prime. Because remember, I don't know what y is. Y is a function in terms of x. So we're saying whatever y is, find the derivative of y, which is just y prime. That's the best we can do. Equals, and what's the derivative of a constant? It's always 0. So now that I have this, now I could solve for y prime. So given this, this implies we have 18y times y prime equals to negative 8x So I just subtracted 8x from both sides, and then divide both sides by 18y, and that means y prime equals to negative 8x over 18y, which then, that simplifies to negative 4x over 9y, which notice how when I found the derivative here, which y prime is negative 4x over 9y, see, this is still the derivative of y. Okay, except if you notice in your derivative, now not only do we have x's, but we also have y's, which that's not a problem, because remember, if I'm trying to find a derivative at a specific point, well, I have an x and a y value, can't I? So I could replace x and y with corresponding x and y values to get what the derivative is, or the slope of the tangent line is, or whatever it may be. Okay, now I want to go to the next page to do part B, and then we'll compare part A to part B, and we'll see how they are in fact the same. Okay, so for part B, what we're doing first is we're not finding the derivative implicitly. In fact, we're finding it explicitly, which is what we've done in this class up to this point. So what we have is, if we have 4x squared plus 9y squared equals to 36, the first thing we want to do is we want to solve for this explicitly, which means solve for y. So if I'm solving for y, subtract 4x squared from both sides, and then divide by 9, which gives me y squared equals to 4 minus 4/9 x squared. Okay, and then what we want to do is we want to square root both sides. And when you square root this, we can put the plus or minus square root of 4 minus 4/9 x squared. Okay, so now I'm pretty much ready to find the derivative of this, which now, notice how this is now explicit differentiation, because I explicitly solved for y. Remember how I was saying, oh, y is a function in terms of x. I don't know what it is. Well, here it is. This is y in terms of x. Whereas in part A, I didn't solve for y. I just said, look, whatever y is, it's a function of its own. We don't have to worry about it. And we were able to find a derivative implicitly. So now let's find the derivative of this. But before I find the derivative, let's just write this in terms of exponential, or give it an exponent instead of square root. So it'll be to the power of 1/2. So to find the derivative, and don't worry about the plus or minus, I'll just tag it along, but it's not going to really affect our derivative. So what's y prime going to be? I have to use the chain rule, right? Bring the 1/2 down, so it'll be plus or minus 1/2 4 minus 4 over 9 x squared to the power of negative 1/2 times the derivative of the inside, which that zeroes out, and then this becomes what? Negative 8 over 9 x. Okay, so that's the derivative, and there you have it. So let's kind of clean this up a little bit, which, what does this become? It becomes plus or minus 1/2 8 over 9x over square root of 4 minus 4/9 x squared. Okay, and so what do I know here? I could kind of distribute this 2 to the 8/9, which becomes what? 4/9 x over square root of 4 minus 4/9 x squared, and then of course I could bring this 9 down. So finally I get 4x over 9 square root of 4 minus 4/9 x squared. And there you have it. This is my derivative of y, and I found this derivative explicitly. Okay, now going back to B, if you look at your notes, you'll see that we got negative 4x over 9y. So let me just kind of write that here. So implicitly, what is it that we got? So implicitly, we got y prime was equal to negative 4x over 9y. Now the question is, wait a minute, these don't look the same. What's the difference? The difference is, and by the way, I forgot to put the plus or minus here, plus or minus, okay? The difference is, over here, I didn't know what y was. Well, guess what? Now I know what y is. If I come back up here, this says, look, if you know what y is, then if you replace it, it should be the same thing as that. Now let's see, what do we get y to be? Y was plus or minus square root of 4 minus 4/9 x squared. So if I come back here, and I replace it, I said negative 4x over 9 times plus or minus square root of 4 minus 4/9 x squared. Notice how this now becomes almost the same thing as that. Now look, what could I do to this plus or minus? I'm multiplying, right? So this plus or minus I can move out front, which the plus with the minus becomes minus. The minus with this plus becomes a plus. So I end up keeping my plus or minus. So this ends up being plus or minus 4x over 9 square root of 4 minus 4 over 9x squared. Which notice how this, in fact, this was my implicit differentiation, but since we knew what y was, we replaced it and we got the same derivative as what we did explicitly. So the point I'm trying to make here is finding the derivative using implicit differentiation is no different than finding explicit differentiation, the derivative using explicit differentiation. The only difference is for explicit, it's nice. The y's are on one side, the x's are on the other. For implicit, everything's all mixed together, which then means y prime will be in terms of multiple variables, where for explicit, it's only with respect to one variable, which other than that, you're pretty much doing the same thing. Okay, so the last thing I want to talk about is the derivatives of inverse trig functions. And now these inverse trig functions, you definitely need to memorize, okay? So the derivatives of inverse trig functions. And the reason why we talk about them here is the way these inverse trig functions, the derivatives are found, implicit differentiation is used. Okay, so we could show them in class and talk about them, but here I'm just going to give it to you. So implicit differentiation is used to prove or find derivatives of inverse trig functions. So I'm going to go ahead and give you the derivatives of inverse trig functions, and like I said, I would memorize them. But if you forget them at any point, you could find the derivative of inverse trig functions without any problems. You just have to use the idea of implicit differentiation. So if you're interested in finding out how, you could ask me in class and I'll show you. Okay, so the derivative with respect to x of sine inverse of x, that's equivalent to 1 over the square root of 1 minus x squared. Okay, and then we have the derivative with respect to x of cosine inverse of x. It's identical to sine inverse, except it has a negative 1 over square root of 1 minus x squared. So it's kind of like if you know sine inverse, then you should know cosine inverse because it's just the opposite sign of it, except people commonly mistake one for the other. So just make sure you know which one belongs to the negative. Okay, and then we have the derivative with respect to x of tangent inverse of x, which that becomes 1 over 1 plus x squared. Okay, and then the derivative with respect to x of cotangent inverse of x, which that's identical to tangent inverse, except it's negative 1 over 1 plus x squared. Okay, and then the other two inverse trig derivatives are cosecant and secant. So the derivative with respect to x of cosecant inverse of x, that's equivalent to negative 1 over x times square root of x squared minus 1. And finally, the derivative with respect to x of secant inverse of x is 1 over x times the square root of x squared minus 1. Okay, so this is a minus 1. Okay, so these are your derivatives of the inverse trig functions. Make sure to memorize these. They'll be important. You'll use them quite often. So make sure you have these down. And this pretty much wraps up section 6. Okay, so if you have any questions, don't hesitate to come by and ask me. I'll be more than happy to answer your questions.